All right, so today we are doing Organic Friday, and we're going to be talking about ethers, an important group of organic molecules. Okay. Ethers are a relatively unreactive group of organic molecules. In labs, they're used a lot as solvents. Right? They're not particularly reactive. It is possible to synthesize them by a variety of methods. That's not really our purpose. One of the first anesthetics that was used in medicine is an ether, specifically diethyl ether. But there's not a lot of reactions that we're going to worry about at this level, all right, in terms of the ethers. All right, so the next slide is really the one you want to focus on, all right, in terms of the functional group. This is really what I want you to know about ethers, all right. There's a carbon-containing group, and organic chemists often talk about this just as R. Okay, so when we say R here, we mean just some carbon-containing group, all right? And on the other side is another carbon-containing group. They may be the same carbon-containing groups. That would be a symmetric ether, or they could be different. So R and R prime can be the same, or they can be different, all right? And then there's an oxygen in the middle, all right? Now, of course, what I haven't shown here are the lone pairs, all right? So we do get this more or less tetrahedral geometry, all right, and a 104.5 degree bond angle around the oxygen. So these are somewhat bent molecules around the oxygen here, all right? I've got a space filling picture down in the model, but really what you need to know about ethers, it's an oxygen with carbon-containing groups on either side, all right? That's really what you're looking for. In fact, if we go back to the previous slide, this was a crown ether, all right? But can you guys see that ether linkage? All right. Here, there's a bunch of ether linkages, and then they're put together in a chain. All right. And that's really what we're trying to get at here. Okay. All right. So, in terms of intermolecular attractions, all right, probably have more detail here than you really need. The molecules end up being slightly polar. All right. But one thing you should realize about this, because of the ROR setup, all right, there are no hydrogens attached to the oxygen, to an oxygen, nitrogen, or fluorine the way you'd need for hydrogen bonding. So ether molecules can't form hydrogen bonds with other ether molecules. Right? They just can't, all right? Which means their boiling points are going to be a little bit lower than, say, an alcohol, all right? They end up being less dense, all right, than alcohols of similar molecular weights, all right. They can accept a hydrogen, all right. So if you have, say, water, all right, and you have an ether, all right, it can accept a hydrogen to form a hydrogen bond from, say, the solvent, if you've got a solvent that can do that, but it can't give away a hydrogen to make a hydrogen bond. So they're not going to be as soluble in water as similar alcohols. All right. So that's more background information. Do you guys all feel you can recognize the ether linkage? That's really the important piece right now. All right. But this might come up in terms of, you know, an example of intermolecular attractions comparing two molecules kind of thing. All right. So the fact that they don't have a hydrogen attached to a nitrogen, oxygen, or fluorine is really the important piece here in terms of the intermolecular attractions. All right. Now, there's actually two ways to name ethers. All right. And I want to just introduce this to you. All right. We're going to do it the easy way. Oops, that's supposed to say way. The easy was, yeah, there's the easy way. Let's fix that. Now, ethers can be considered symmetric, where you have the same alkyl group on either side. All right, so here's an example of a symmetric ether. There's a methyl group on the left of the oxygen. There's a methyl group on the right of the oxygen. All right, it's two methyl groups, so we call it dimethyl ether. This is the sort of easy name, the common names for ethers. All right, for an asymmetric ether, again, you have to look at what the alkyl groups are. Here we have a methyl group, yes? And here we have an ethyl group, but we'll list them in alphabetical order. So this could be ethyl methyl ether. So that's the easy naming system. And it's really very commonly used, especially for small, simple ethers. All right, but that's not the official name. The official name's on the next slide. I'll get to that in one sec. Okay. All right, are we ready? Okay. So the official naming, all right, would be, all right, to draw the simpler alkane, sort of draw the simpler alkane on the left, just to make it easy for yourself, all right? And then you name it as an alkoxy alkane, all right? So for example, if we go back to the dimethyl ether that we had just looked at, all right, this part that I've highlighted in blue would be the methoxy. And then this would be that's a methyl derivative. So methoxymethane is where that's coming from. All right, saying there's one carbon on the left of the oxygen and one on the right. And so the IUPAC naming system does this alkoxy alkane method. All right, and you would always do the simpler alkyl group first as the alkoxy, and then the more complex part at the end of the name. All right, so it's easier to draw that on the left. All right. But that's not very difficult, is it? All right. Really, the basics of the naming is quite easy. All right, so let's name some compounds. All right, we can name it with both systems. All right. So let's look at this one. We have CH3O, CH2, CH3. All right, what's this group? Methyl. All right, what's this group? Methyl. All right, so this would be, we could call this ethyl methyl ether, but what would the IUPAC name be? Hold on. Methoxyethane. Yes? Okay. Let's look at this one. We have here 2 carbons, that would be an ethyl group, right? And on the other side we have 3 carbons, that's a propyl group. What would the simple name be? It would be ethyl propyl ether. What's the IUPAC name? Ethoxypropane. Whoops, I wrote it wrong. Ethoxypropane. Excellent. That's not too bad, is it? All right. But really, right now, our purpose is just recognizing these, all right? And just doing some simple nomenclature. All right. Do you guys feel you can name them if you press? Okay. Now let's draw some structures. If you have methyl hexyl ether, what would that look like? How many carbons in the methyl group? 1. How many carbons in the hexyl group? 6. All right, and then there's an oxygen in between. So depending on how you draw it, it's probably easier to just draw the carbon backbone. All right, or you can do we learned that up and down with the lines, but I'm having a hard time drawing that today. All right, that would be the backbone, and then we can put in all the hydrogens. All right, for propoxypentane, how many carbons in the propyl part? Would be 3. How many for the pentane? 5. All right, so you might have something. I'm running out of room. Something like that? Are we good? Excellent. We'll stop here.